Hello and welcome. Have you ever looked at the branching patterns of trees, the structures of snowflakes, or the jagged edges of coastlines and wondered if there was a hidden mathematical order behind them? Today, we're exploring fractals, intricate patterns that repeat at different scales, appearing everywhere from nature to cutting-edge technology. In this lecture, we'll define what fractals are, explore their mathematical foundations, examine their historical development, and highlight their fascinating real-world applications. As for the definition, fractals are geometric patterns that exhibit self-similarity, meaning they look similar at different levels of magnification. This doesn't necessarily mean they're identical at every scale, but rather that the mathematical processes that generate them create structures that resemble themselves at all levels. Benoit Mandelbrot, the mathematician who popularized fractals, summarized them best in his 2010 TED Talk, Fractals and the Art of Roughness, in which he says that they are like the whole, but smaller. This property of self-similarity often arises from relatively simple mathematical rules, yet it can result in highly complex structures. This cauliflower exemplifies this concept with its repeating nodes that exist seemingly at every scale. At this level, it looks almost alien. Fractals in nature have always had a deep connection to chaos theory, which studies how complex patterns emerge from seemingly random systems or occurrences. One famous example is the coastline paradox. The more precisely you measure a coastline using smaller and smaller increments, the longer it appears. Since this process can continue indefinitely at smaller scales, we recognize that natural coastlines exhibit fractal-like properties. There are so many factors that influence the erosion and buildup of a coastline. There's a certain degree at which chaos gives way to seemingly infinite phenomena. More examples of this include flora such as trees, ferns, and cauliflower, which grow in self-similar patterns, optimizing light capture, and nutrient transport. Additionally, mountain ranges, river networks, and fault lines display fractal behavior, influencing erosion patterns in landscape formation. However, in nature, fractals are not always infinite. There is always a physical limit, such as the molecular structure of a coastline, that prevents endless detail. This is where the concept of fractal dimension comes in. Unlike traditional geometry, where objects have a whole number of dimensions, for example, a line is one-dimensional, a plane is two-dimensional, fractals exist in between dimensions. A coastline, for example, cannot be strictly classified as a one-dimensional line or a fully enclosed two-dimensional shape, because its measured length depends on the scale used. To quantify this, mathematicians used the Hausdorff equation, given by d is equal to the natural log of n over the natural log of s. N is the number of self-similar pieces, and s is the scaling factor. When used to measure the fractal dimension of the island of Great Britain, for example, we get approximately 1.25. An island coastline can be differential depending on the scale used. However, without being able to go to the atomic level, the arbitrary scaling makes it very difficult to get an accurate picture for the length of the said coastline. The length is seemingly infinite, even though it's perfectly conceivable for an island like Great Britain to fit entirely within a finite two-dimensional geometric shape. Famous examples of fractals include the Mandelbrot set, defined by the equation Zn plus 1 is equal to Zn squared. This infinitely complex shape emerges from simple iterative calculations and has intricate, self-similar patterns at every level of magnification. There's also the Sierpinski triangle, which follows the formula n is equal to m to the power of d, where n is the number of pieces, m is the magnification level, and d is the fractal dimension. This triangle can, in theory, be divided infinitely while maintaining its self-similar pattern. There is also the Apollonian gasket, denoted by the formula K1 plus K2 plus K3 plus K4 squared is equal to 2 multiplied by the same thing, but with K1 plus K2 plus K3 plus K4 all squared themselves. It's somewhat similar to the Sierpinski triangle, but instead composed of a seemingly infinite array of tangent circles. The equation for this fractal allows us to calculate the radius of a new circle from the curvature of 3 known circles. It's also one of the earliest known examples of a fractal discovered. Other well-known fractals seen here include the Koch snowflake and the Barnsley fern. As to the history, the concept of fractals has roots in earlier mathematics, but the term fractal was coined in 1975 by Benoit Mandelbrot. He built upon earlier works by mathematicians such as Gaston Julia and George Cantor, who studied self-similar and non-integer dimensional objects. However, it was Mandelbrot's work that unified said research and showed how fractals appeared in both mathematical theory and nature. As for the applications, fractals aren't just theoretical constructs. They have uses in various fields. In video games, for example, fractals are used to create realistic landscapes in games like Minecraft and Skyrim, where mountains, trees, and terrain are generated using fractal algorithms. In biology and medicine, the structure of blood vessels, lungs, and neurons follow fractal patterns. Fractal analysis helps in tumor detection by identifying irregular growth patterns. In urban planning, cities often grow in fractal-like patterns themselves, and these patterns influence traffic flow and infrastructure planning. In meteorology, fractals help predict hurricanes and weather patterns by modeling cloud formations and atmospheric turbulence. This will likely play an even more crucial role in the future with the rise of climate change. In environmental science as a whole, fractal analysis is used to study coastline erosion and climate change and the effects of climate change on landforms. Thank you for watching.